Now, this goes a long way back. I was at the back end of the time that I spent at SEPA, which was a long time, looking for copper in the Capricorn origin, following a sediment-hosted copper model, but I never believed it. And the geochemistry, which, as you know, OSNACA was a thing by then, it had a really magmatic flavour. Any copper mineralisation you could find was telling a different story. And later I would join CSA Global and speak to the basin-hosted base metal experts who said completely the wrong sort of basin. There's no rift, it's a gentle sag. Anyway, then came the seismic profiles that went through there and showed these cratonic sutures. And so the heretical thing that I'm going to tell you is that Abra has a lot more in common with Olympic Dam and vice versa than most other ore deposits, including almost all ore deposits in a subduction-related setting. Because the key to understanding this unruly clan is intracratonic. You can put away your subduction models, and they're what have got us into so much trouble misclassifying these copper-gold systems. I'd like to acknowledge my co-author, David Groves. He gave me the best field area in history for a PhD 30 years ago plus. And I thought, well, I can't really write a paper by myself because I'm not clever enough, but I thought if I could grab someone to help, a fitting person to write that with is David, because so many of the ideas that have come from his writings on IOCG deposits, and then some other suspects in here who are acknowledged in the paper we've got. Jim Thornett and John Hronsky, they have also aided this paper a lot. We know this is from Groves and Santosh. I think this is pretty well understood and it works. The relationship between VMS deposits, porphyry copper, epithermal, and that's at one snapshot in time, so we understand things spatially in subduction-related systems and temporally. So we have the early VMS, the porphyry copper, and then the deformation with the orogenic gold and the collapse, your late forming systems. And that checks out very well. The only problem is applying this to ore or mineral provinces where there's no active subduction at the time of mineralisation. And so this is the six blind men and the elephant. If you look, and I have Abra in mind because it is the perfect example of finding pieces of evidence that partially fit the model. So we find a metal sweep which almost fits VMS except for the tungsten, veins, coliform veins, breccias, bedded or laminated massive sulfides. Take your pick. And Abra has been described in the literature as a shale-hosted massive sulfide, stratiform copper, VMS, IOCG, intrusion-related breccia system, and epithermal. And there's reasonable grounds for calling them any of these things. So Ross Large, I remember at the SEG in 2004, came up with a triangle below with these different fluid systems and plonked Abra fairly close to the middle of the triangle between ZX, epithermal, and VMS. All these, except for the IOCG, are subduction-related systems. And that's why, if this contribution does turn out to be helpful, it's helpful because the key link is the intracratonic connection. So we'll get rid of this, get rid of this, and we're going to fill in this intracratonic copper-gold set of criteria that link Olympic Dam at one end of the spectrum to Abra and Prairie Downs at the other. So we need some unifying principles, something larger than IOCG or any of the, and that incidentally, IOCG is the only acceptable mineral deposit model, and it's a pretty unruly class with lots of arguments around the edges. All the other mineral deposits that we're going to just look at here don't have an adequate mineral deposit class yet. In fact, there's all sorts of things we don't know, and there's an extensive list of further work that encourage people who are interested in these things to go on with. But what are the things that we know about these systems that are the same? They all lie in the hanging wall of a cratonic suture. Now, a cratonic suture is a very important break in the lithosphere where one piece of continental crust has been brought alongside another, collided with, owing to subduction, which does two very important things. All the way along that conveyor belt, the mantle wedge underneath that hanging wall is fertilised by fluids streaming off, just as we know in our subduction model for deposits that form during the subduction cycle. But that metal is trapped there forever, unless it's released by a later mineral system event. And you've got a really important plumbing system, which is that cratonic suture and the related transform and parallel faults. So you've also got a structural architecture, particularly in the hanging wall, that's going to be important for focusing. Hundreds of millions of years later, in the case of the Paterson province, over 1 billion years after the collision, we have a pulse of heat, and the heat is everything. Large heat pulse, large copper gold province, small heat pulse, small copper gold province. That burst of heat is what stirs up the metal in the mantle, and this is a big area for future research. We really don't know very much at all about moving that metal out of the mantle, transporting it all the way to the upper crust. But what looks very clear, at least to me, is that the coeval felsic intrusions are not the metal source. And it's so tempting to say, well, there's the source of the metal. I've got this magmatic metal signature with copper, gold, bismuth, tungsten, selenium, stinking magmatic, and I've got these coeval intrusions. So in the Paterson province, the Crofton Sweet granites, they are formed high in the crust. They're shallow melts, whereas the juice is coming from that fertile mantle. Although there's quite a range in metal signature, the key elements are those first 5 in particular, and then indium, moly, tin. And then if there's enough hydrofluoric acid to leach from whatever country rock is around, you can get cobalt, nickel, platinum, palladium from ultramafic rocks, or uranium rare earths, as we get at Olympic Dam and some of the other large IOCG deposits. Those secondary leached metal associations are really only with the big IOCG deposits and other rare beasts. Once you get more convoluted fluid paths through the crust, you tend to lose that and you pick up more lead zinc, which really is incidental to the story. Okay. When you get that pulse of heat, you're going to get things like carbonatites and lamprifiers, but we don't tend to see much evidence of them. The one place where we see it at the deposit scale that we know of is Olympic Dam, where there's abundant lamprifiers in with the granite that's all been brecciated and completely destroyed by hydrofluoric acid and the ore fluid. What does appear to be very important is fluorine. That seems to be the master key. There's been a lot of debate, but it seems increasingly that in the orogenic gold system, we're talking about a very similar fertile mantle scenario, but it's sufficient just to have a CO2-rich fertilised mantle. If you're going to move copper along with the gold and these other metals, it does seem that fluorine is important. And I learned through reading up on this, Olympic Dam, all 8 or 11 billion tonnes of it, is about 2% fluorite. There's the residue from having a bath, an absolute bath in hydrofluoric acid. So although we don't see fluorite much other than in the large IOCG deposits, it does appear to be a key to moving that metal out of the mantle and getting it all the way up to our deposit sites in the crust. But as I've emphasised in blue down the bottom, that journey from fertilised mantle to deposit site has lots of unknowns. All right. So now let's fill in the spectrum of deposits. So we've got Olympic Dam at one end. So there I've drawn a very fat arrow going straight up, forming vertical breccia pipes. So that's the most direct route from your metal-rich fertilised mantle. You've got your fluorine, let's go. And, you know, it ascends from the mantle up to the upper crust in a single afternoon, and we get something beautiful like Olympic Dam. Move along, and we have less heat now to drive the system, but we've still got, and this is important, a silica undersaturated system. We're coming from ultramafic source, the mantle. So we get these ironstones, but we don't get any quartz veining of note. If it's quartz veining, it's later. But we get smaller ironstone deposits like Tennant Creek and Stara. They're more structurally controlled. You'll see them sheared, brecciated, but not milled brecciated. There's not the same violence, if you like. And then we pass across to where we now start seeing quartz vein arrays. So we've still got the same, much the same metal signature. Telfer, Winu and Havieron, they're all cobalt rich. And they've also got the copper, gold, tungsten, bismuth, etc. And we get a variety of styles. We start seeing bedding parallel zones with not much quartz veining or none at all, where we've got disseminated or even massive sulfide along the bedding. We get breccia pipes, especially at a Havieron, and quartz vein arrays. But we've reached the silica saturation stage. And then once we get to Abra, they're not even copper gold deposits anymore. So I had blazing rows with my co-author about whether we should really put this in at the end of the spectrum, but it belongs there. And I think to understand success, you need to understand failure. And the Abra Prairie Down ends of the spectrum is a failure. They're not economic, really, you could argue, but they're not as economic as Olympic Dam or Telfer. The problem with those systems is that they're starved of heat. It's enough heat to prove the concept, but not enough heat to make large economic copper gold deposits. They've got the copper gold flavour, but the economic metals are now lead and zinc, things that have been picked up in a very convoluted hydrothermal flow path, lead, zinc, silver. So we've got different shape deposits, we've got different ore textures, and the metal signature, the further we move towards Abra Prairie Downs, the more of the blue type, the blue font, the lead, zinc, etc., which is nothing to do with the fertilised mantle. That's very likely from the crust because we don't see it in the Olympic Dam end member. And we even pass out of having copper and gold being the dominant economic commodities when we get to the Abra Prairie Downs end of the spectrum. And as I've been saying, the amount of heat is the master variable that controls all of these things. So here's a cartoon diagram. We're going to look at, it's got two panels, the cartoon. This is the original collision. So we're taking a snapshot just as the last of the oceanic crust disappears down the plug hole, down the subduction zone, and we form a new cratonic suture. And that forever freezes into place that tectonic architecture of that reverse fault, back thrusts, transform faults, that's all there in the hanging wall. And the granitoids are from deep in the crust, and we'll have a look at what that means when we get to the geochemistry of the granites, but that's your subduction-related magmatism. But there's our goodies. It streamed off the hydrated slab and fertilised that mantle wedge. Hundreds of millions of years later, we might have some subduction here it's shown on the cartoon, but it's away from the main game. The important part is where it says heat, and we've got those arrows. And that heat causes, we call it an asthenospheric upwelling. So that's structurally important. It's extending and thinning the crust. You put all that heat high up into the lithosphere, you get a different type of magmatism. The felsic magmatism, now the melt is shallow in the crust. And that's those yellow plutons there with the blue arrows with a short path from source to emplacement of the granite. And that heat also moves the metal out of the fertilised mantle and up to the deposit sites. So yeah, emphasising again that the shallow crustal melting is another feature of that high heat flow, but not the source of the metal. It's just coincidental, coeval, but not genetically related to the metal in the deposits. It's a mantle-derived ore fluid that is making its way from the mantle to the deposit site without any crustal level magmas in between. And here's the key figure. It was a joy to put this together and discover that the Gawler, Cloncurry, Tennant Creek, Patterson, and the Capricorn all have this beautiful wealth of geoscientific data, seismic traverses across all of them, where the cratonic sutures have been nailed down, not just with that seismic, but with beautiful dating and isotopic work. There's so much geoscience here that we can, geoscience data here and good work, that we can confidently place the cratonic suture. And what do you know? The intracratonic copper gold province is in the hanging wall. I thought, just near the cratonic suture. That was my model for over a decade coming out of the Capricorn. And you'll notice that Prairie Downs is just in the hanging wall to the Bearing Downs suture. Abra is pretty well right on the Lions River Fault. But in all the other districts, from about 20 to 100 kilometres into the hanging wall of that suture is where we find our copper gold deposits. So that's a really important commonality between all 5 districts. We get a variety of expressions of all the different metal signatures and deposits, but where they sit in relation to that cratonic suture in terms of both space and time is the same. Bit too busy, but what I've done is I've expanded the key part of the Gawler, Cloncurry and Tennant Creek tectonostratigraphic frameworks. Don't get too caught up in it. The key features are, where's the suture? So we've got the Elizabeth Hill, the Gidya, the Galungaroo, Camel Tabletop, and there's 2 sutures that formed at different times in the Capricorn. We know that they are at least as old as shown there on the time chart, at least some hundreds of millions of years later, but in the case of the Patterson, more than 1 billion years later, is the intracratonic copper gold mineralising event, highlighted in yellow. And again, with all this beautiful geoscience data, at least one, but and that's the case in the Capricorn, but in all the other districts, there's multiple deposit dates, and they're in that time bracket of the intracratonic felsic magmatism. So there's a beautiful spatial but also temporal relationship. The suture is much, much older. The mineralisation is late, which is why these things are commonly undeformed, and if they are deformed, it's pretty well the last act. And that's where they sit. So we'll go back to this map, and now we'll see that the Gawler, the felsic magmatism, the Gibraltar sweet granites and the the volcanics, the Gawler volcanics and so on, that's 160,000 square kilometres. That's the largest felsic intracratonic province in the world, I think. Massive, massive heat flow gives you the hugest deposits and the largest felsic magmatic footprint, and some subordinate mafics to go with it. Cloncurry, Tennant Creek, Patterson, between 6 and 15,000 square kilometres, sub-equal, very decent. You can get an Ernest Henry, you can get a Telfer, you can get a Winu. The volcanics, which we can pin at the same age as Abra, the date is pretty poor. It's a plus or minus 20 or 40 million years, but it's also the textural, it's the geological relationship of that rhyolite to the stratigraphy into which Abra is placed. That is coeval, 6 square kilometres. There's just not the heat pulse to do the business. And you can see there are those tiny red dots all over the Capricorn. That's the extent of copper gold mineralisation with that magmatic signature. There's some recent work going on in the East Capricorn that shows that things mightn't be so bad over there. There might be a bit more prospectivity, but I would have to say that for something that's as well exposed as, or better exposed than the Cloncurry district, we're not going to be finding great big things in the Capricorn, and I think that this model explains why. There's just not the size of thermal footprint expressed by felsic magmatism to expect the copper gold mineralisation to go with it. So we can show copper and gold endowment charts, the tonnes versus the grade. Olympic Dam, of course, is the big daddy for both copper and gold. But even taking Olympic Dam out, the Gawler Craton stands apart in terms of copper, but the Patterson province is not too shabby in terms of gold. There's a lot of gold up there. Another way of expressing that is then versus the scale of the igneous province. And if you look at that orange dot for Tennant Creek for copper, you might say, that's a big enough igneous province. Is there some copper that hasn't been discovered there? Well, the Tennant Creek supersuite has recently been realised to be much bigger than was previously thought. There's an awful lot more of it undercover, moving east towards Georgetown, and that mightn't be a bad place to explore, except it is under a few hundred metres of cover. All right, we've only got 5 points. Between any 2 points, you can draw a straight line, but with Abra type at one end of the spectrum and Olympic Dam at the other for Gawler and Capricorn, we have a relationship that the other 3 points fall roughly on. As we get more districts recognised around the world, we can flesh this out, but I think there's very good evidence that the size of that felsic igneous province dictates what you can expect in terms of total copper gold endowment. So this is the Osnacker collection, was where the geochemical data we're going to look at. So it was fun to finally make some use of that collection and go down and photograph some of them. So what we see in the large IOCG deposits are these milled textures. It's not just a breccia, it's incredibly aggressive. Olympic Dam at least, and perhaps some of the others, we've got hydrofluoric acid aiding that process by dissolving the rock pretty well and replacing it with this ironstone and copper sulfide matrix. Moving across to the smaller ones, the Warrego is more of a jigsaw fit breccia. Yes, it's a bit violent, but not nearly as violent because the oomph is no longer there. We start to see sheared textures like gecko and then a massive ironstone at White Devil, notably with more than 1% bismuth. All that silvery stuff being bismuthinite, a bit too small to see, but there's visible gold shown there at White Devil as well. So a change in texture from the large IOCG to the smaller IOCG deposits. And then once we reach silica saturation, I've only got examples from the Patterson province from Telfer, but we've got the quartz adularia veins there, a very sulfide-rich vein, but there's a little bit of quartz on the edge there where it says chalcopyrite, and then also a lot of sulfide replacement. So although there is quartz veining, there's also a lot of silica undersaturated sulfide replacement of the carbonatic fine-grained sedimentary host. So that's the large copper gold side in veins. And then the smaller system, suddenly we see a lot more base metal. So beautiful coliform epithermal-like textures at Prairie Downs. It's fair to call it epithermal in terms of texture, but it's got nothing to do with epithermal in terms of its tectonic setting. And then here at Abra, there's the deep crustiform veined, more copper-rich stockwork, which is not of high enough grade to be mined, or it's too deep anyway. But beautiful rhythmic textures with quartz and carbonate, and then a massive sulfite there with magnetite and galena, and a little bit of small dark red bits of hematite. So a real range of ore textures, but they're reflecting the amount of heat in the system. This is my bag. So this is not using the Osnacker transform, it's just normalizing the abundance of metal to average crustal abundance so that we've got comparable plots that aren't too complicated. So the first thing to note is the classic rabbit ears. So if you pick out copper, silver, gold, copper's a peak, silver is highly enriched, but not as high as copper and gold. So there we're going to see that rabbit ear profile over most of these deposits because they're copper gold systems. But the top three, Olympic Dam, Prominent Hill, Ernest Henry, we've got the lanthanum uranium enrichment. In some of them, we're going to see some cobalt or some nickel, particularly in the Cloncurry district deposits. So there's quite a lot of variation, but I've highlighted those key, what we would call normally magmatophile metals that we would normally use to diagnose a magmatic fluid. The copper, the gold, moly, tungsten, bismuth, selenium, and so on. And they're featuring through all of these, and they go on to feature. So Merlin's this crazy moly deposit, but the key to it is what goes with it. It's not economic, but there's gold and there's selenium and there's copper and there's tungsten and there's bismuth. It's got all of those metals in its signature, along with some platinum. What is that doing with a molybdenum deposit? Finally, the rabbit ears break down when we get to Abra and to Prairie Downs, and we can see that there's actually a little silver castle. The silver is now relatively more abundant than the copper and the gold, except in the Abra copper mineralisation shown in red. So there's a sensible progression or variation as we go along the spectrum of the intracratonic copper gold clan. The only really important thing about this is the heavy rare earth element profile. They're all flat. And what a flat, heavy rare earth profile means is that the melting's shallow in the crust. The only exception here, for the data shown here, is that single sample of Olympic Dam lamprifier. Well, that's not an upper crustal granite, that's a magmatic melt, so it has that steep, heavy rare earth element profile. But everywhere else, each of these districts has that flat, heavy rare earth element profile. It's not strange, but it is less common than what we would see across all the granites in Australia. So here's just the copper gold province data, plotting close to the within plate granite field and the collisional field. So there's our data there, and we can compare that. I might just go back and forth a couple of times. That's all the granites that I've got data for in Australia, and I'll show you that data in a minute. So, oops. So that's the flat heavy rare earth, copper gold province data up there. Oh, Jesus. And then that's our much more common subduction related signature. So it's a different type of magmatism to what builds most of the crust. I had good reason to finally bite the bullet and get not only the Geoscience Australia data, but all the other surveys that I could sensibly get data out of. And being the database administrator wizard that I am, I compiled all this in Excel by myself. You're welcome to the compilation. I tried very hard to keep it as clean as I could, and thankfully it's led to Geoscience Australia doing a project which is to standardise and make much more user-friendly the data that comes out of the various surveys. But if you want to take a shortcut and all my errors that go with it, you're welcome to this compilation if you've any use for it. This is the only part that Dig would approve of, because he only likes talking about big ore deposits that are famous. We're in Carajás now. Carajás does not have the seismic profiles. There's not the same. There's been a lot of research there. I don't know any of it well, but it has not matured scientifically to the same stage as those 5 Australian provinces. But there's an amazing variety of intracratonic copper gold deposits there. And this is the one that didn't fire once, it fired twice. How cool is that? It's Archean and then early Proterozoic. So we've got mineralisation at about 2.75, and then there's more mineralisation at about 1.88. But not only do we have classic IOCG deposits, like Sasego and Salobo and Cristalino, we've got these other weird beasts like Serra Pelada with its gold, palladium, platinum in extraordinary abundance. What's with it? Bismuth, tungsten, selenium, etc. Jaguar, which Rocky knows well, he's worked on this, a nickel cobalt with bismuth, tungsten, selenium. It's not a magmatic nickel signature, it's a hydrothermal nickel deposit, and it happens to be where there's ultramafic rock in the stratigraphy, so you don't need to imagine too hard where those ultramafic sourced metals have been leached from by that aggressive fluorine-rich fluid. And we've also got copper gold quartz vein deposits as well. They're all 1.88. So this would be a fantastic place to really get in and understand more about, well, where is the suture, or where are the sutures, and so on. But from what little I know about it, it's a really be a wonderful place to go and work. I wanted to leave this out because the Andean IOCG deposits are subduction related, so I could conveniently ignore them. Jim Thornett was kind enough to read an early version of the manuscript and said, "Carl, this is not acceptable. You know what an aggressive fella Jim is. He wasn't going to let it go." No, it was really good. He said, "Carl, I've got some stuff here, read it, because there's so much in common with what you're saying." And what I learned from it, and I don't know much about it, is if you look at step B, so there's the early Cretaceous, and then in the mid-Cretaceous, the slab rolls back. And what happens? The back arc extends, the asthenosphere wells up, we get shallow crustal melting, those granites will have flat, heavy rare earths, and we're getting these ironstone-hosted copper-gold deposits with all that suite of metals. So it makes sense to my mind that this is exactly the same thing going on in an unusual subduction-related setting. It's like we're having a brief intracratonic period in a subduction evolution. So it is possible, but to my knowledge, this is the only place that we know of clearly that this has happened in between active subduction. These are the models that the workers have tried or have put together to try and explain what's going on. And I think this insight would be very useful, because what they're talking about is having a diuretic or maybe even more mafic magma and an immiscible iron oxide melt. Now, I'm really uncomfortable with that because I don't know many of those. I think what they've got there, it's unusual because in the intracratonic setting, the copper, gold and iron oxide juice coming straight from the mantle doesn't have anything to do with the coeval magmas, but it looks in the Andes that it absolutely does, because they have mapped these beautiful transition from iron oxide apatite deposits through to ironstone breccias with IOCG mineralisation. But they're still talking in terms of the magnetite bodies being magmas. And with absolutely no right to say so, I reckon that's bullshit. I reckon that's... from everything, for all of this work, screams to me that magnetite and the metal with it has got nothing to do with that barren diuretic magma. That diuretic magma has been fertilised by mantle juices. Interestingly, John Wronski said, "Show me the fluorine. Where's the fluorite?" So I desperately searched around all the deposits to no avail. Well, what about if we did a project to look at the fluorine content of the apatite? Would it be expressed in something less obvious than just fluorite? It's a real conundrum to me as to getting that such a similar signature in a very similar tectonic setting, albeit in a subduction-related setting. There's too many problems for me with having that being an upper crustal magmatic story. All right. The grand cartoon. And it's all about heat. As heat decreases, the fluorine budget collapses. With fluid pressure and speed of ascent, we get a different, changing deposit overall form and textures within the deposit. The size of the intracratonic felsic province decreases. The deposit, the size of the deposits and then the overall tenor of the whole province decreases. The only thing that increases with decreasing heat is the amount of crustal contamination by lead, zinc, cadmium, arsenic, etc. The uranium, lanthanum and the nickel cobalt actually is only a feature of the high fluorine, high heat flow. So with that cartoon there and the heat lever, you can pretty well explain all the variation there going across the full gamut of deposits that I would say for most people would not have expected to put into a single paradigm. And mercifully, we've taken it out of the subduction related set of ore body models where they just don't fit. All right, we've got Telfer type with, at my count, 3 big examples: Telfer, Havieron and Winu. An obvious next place to go for me would be Carajás. If a sufficient number of quartz saturated intracratonic copper gold systems are documented, we might be able to flesh out the new ore deposit models that are required to properly describe the intracratonic copper gold spectrum. That's just one major axis. There are other minor axes of variation, like the nickel copper, platinum palladium, the highlight being Jaguar, the moly-rich version, the serrapilladas or the ocaligans. I think we can fairly neatly fit all these in, but there are other minor axes of this spectrum. I'm referring to that mantle fluid as purple juice, nodding my cap to John Walsh, who, so far as I know, was the first to coin the term black juice for this mantle-derived orogenic gold fluid. And I was saying before, it sounds like that needs CO2 rich, but if you're going to start moving copper as well, it looks like you need fluorine. So let's call that purple juice. But how does that work? I don't know. And I'm not the person to ask because I go all very quiet when people start drawing phase diagrams on the back of envelopes. But somehow we need to explain how that metal remains in solution, not just for an IOCG, a large IOCG, but for the full spectrum. I mean, that's a big job to keep that metal in solution from the mantle to precipitate at Abra or at Prairie Downs. And are the metals liberated by devolatilization, which is what I would guess, or are we talking about ultramafic magmas that are giving off a fluorine-rich fluid? That seems unnecessary to me. If we've got purple juice and black juice, can we start mapping? Well, we can define these different types of fertilised mantle. Can we even start mapping different domains of fertile mantle? And one hint to that, again, from John, is that one of the deepest metamorphic reactions or devolatilization reactions is the breakdown of phlogopite, which is rich in fluorine, which explains why we're getting our big deposits. You know, they're not on the suture. You need to be far enough back, with a decent distance above the fertilized mantle, and that's where the fluorine is going to be most liberated from the deeper parts of that fertile mantle. Perhaps. All right, this is what I like. Exploration implications. Well, if this model is valid, I think there's a few things. The first is to stop using inappropriate deposit models like porphyry epithermal, orogenic gold, VMS, etc. And those targeting criteria sometimes do a bit of the job, but they're not. Hey, that's my joke. And what it's going to do is it's going to direct your attention to what actually matters, because exploration implications have to matter to somebody behind their exploration desk who's about to go out to the field. And I think the things that you need to know is you must show that the deposit ages map the intracratonic magmatism age. Once you've got that, that's enough. You don't need the seismic data and all the rest of it to prove the cratonic suture and everything else. If you've got something late in the cratonic history, you're intracratonic, and it's got that, the ages match and the metal signature matches, that's probably enough. And then the key thing is how big is that felsic province, because that's the key. If you run into lead zinc rich mineralisation, that's a bad sign, I would say. We've only got a population of 1, but you may have found yourself in the Capricorn. Except for the East Capricorn, that's a lot better. No, the West. And then geochemistry. Yeah, what I'm saying there is that quick work, the geochemistry, the geochronology, and some quick mapping is going to be much faster to identify the key features that you've got an intracratonic copper gold system and that's the way you should be exploring it. It's going to be a lot quicker than magnetotellurics and seismic and the really detailed survey style mapping, because I'm thinking overseas as well. And something about these systems, which we're about to see now, is you don't need to wheel out your Yulgan orogenic gold drilling grid. The footprints of the big ones, the Telfas, the Winnus, especially Olympic Dam, they're huge. Wide space drilling is going to get you onto these things. You don't need to be running along D3 shear zones with 200 metre spaced lines and 50 metre spaced holes. These deposits have large footprints. So here is the GA Australia-wide cratonic suture map for major crustal breaks. It doesn't agree perfectly with the West Australian version. So there's some things to be done there. But since putting this together, I can think of 3 very likely other intracratonic copper gold provinces in Australia. And if only 1 or 2 of those are correct, well, that's 6 or 7. These things must be all over the world, particularly in the Proterozoic. But Karajas shows that they can be in the Archean, and the Andes show that they can be in the Phanerozoic. I've got one little red diamond up there, which is the Red Bank Breccia system. I think that may be one. But we could say where in the world? Yeah, where to next? But Derek Marshall very kindly has allowed me to show you a few slides here of their Christmas Creek project. And that's in a very nice regional structural address at the elbow of the Kimberley, where the Halls Creek and the King Leopold origin meet. But key to me is that the suture shown there, I can't remember its name, unfortunately, dips to the north. Derek's project is in the hanging wall to cratonic suture. So straight away, I'm really, really interested. And what little data I've got, the Sally Downs super suite, I haven't got ages yet, but it's a nice flat, heavy rare earth element signature. So I'm thinking, okay, this could be interesting. So I looked at his drilling data. Just look at, well, where the rectangles are. There's a high bismuth with gold versus a lower bismuth with gold signature. And where's arsenic gone? Yeah, no, that's all right. So we've got 2 different styles of mineralization signatures. And then on the next graph, we're going to put lead versus everything else. And we've got lead above 100 with not much arsenic, and then high lead arsenic. So that's just giving us the different flavored mineralizations in the drilling. Keep it simple. The Coogan prospect has been drilled here like you might do some early stage reconnaissance over an orogenic gold system. Traverses a few hundred meters apart and holes reasonably close together. Every single hole there that is more than 100 meters long, and most of them quite a bit less, gets some evidence of what I think is an intracratonic copper gold system. The core of it has exactly the right signature: gold, bismuth, tellurium, selenium, copper, moly. Dead ringer. Unusually, or perhaps unusually, it's got a lower temperature halo of low arsenic but high lead, zinc, cadmium, silver, indium. If you take both of those together, what you could do is you could drill 1 hole every square kilometre and screen that whole area. Just a different exploration approach. It's not for small companies or very small companies, but really the amount of stuffing around we do, wouldn't it be nice to be able to screen 1,000 square kilometres of prospective intracratonic copper gold territory with 1,000 100-metre long RC holes? Ooh.